said the convention for electrons and protons, what you said, the positive and negative. So you should be thinking in the direction of symmetry. Okay, the previous webinar what we had conducted on some of those symmetries as well. Okay, in the concept of symmetry, there is a proton and antiproton, there is electron and anti-electron that's been produced. So there is a possibility of existence of both. But what about the magnetic lines? Even that's been experimentally proven. But in the CRN and all. But what about these things? So that is one of the question what I was having actually. But I don't know. Yeah, there is no experimental proof about that, which says that okay, magnetic lines of fields are having this kind of symmetry. No, we don't have that. Fine. Well, there is a chaotic behavior in the magnetic lines, as you see over here, including the gases and the dust that are having the interstellar surface. I mean, the sun's surface, the gases, whatever you can see over there, right? Yeah. Similarly, the fluid turbulence, okay, the fluidic turbulence or the gaseous turbulence, you can call it. It's a CFD simulation, okay, it's a CFD simulation of the water, or it's a CFD simulation of the liquid or the fluid that we are considering. Okay, fine. The same way you can see the turbulence in the sky. Okay, I put this painting particularly to indicate that turbulence there. Okay, so the turbulence in the sky, the turbulence in the gaseous clouds, okay, the turbulence in the gases and the atmosphere of the earth. Okay, fine. So well, before moving to all these things, okay, you can see a pattern, right? The magnetic field of the sun, the atmosphere, and the chaotic behavior of the fluid, all behaving in a similar fashion, right? What is that? What is the common characteristic of these three guys? What is the one common characteristic you can consider? Yeah. What by just looking at this picture, okay, by just looking at these images, all three are having some turbulences and some kind of disturbances in it. So based on that, can you say like what would be the commonality? I mean, what would be the common behavior of these three different photos what I am showing here? Yeah, anybody? It's the turbulence and the fluid motion. Okay, it's the turbulence and the fluid motion that is present, that a commonality between all these three photos. Okay, all these three pictures. Okay, now, okay, we'll come from once again with this image. Okay, here we are having magnetic field which are behaving in the form of turbulence. Okay, can we say that magnetic field can be modeled with the help of turbulence? Well, that's what it is called as magnetohydrodynamics. Okay, and in the end we will be looking at that as well. Okay, but before that, how the magnetic fields are generated, guys? There are a set of equations called Maxwell's equation. I hope everyone is familiar of those equations. Okay, so we'll open up those things as well, right? So these are the Maxwell's equations. Yeah, first equation determines the Gauss law. What does it say, guys? Gauss law. Yeah, anybody? The Yeah, anybody, the PhD candidate in our call can answer, or else the other people can also answer. Yeah.
It's the easiest way to predict electric field due to complex charge system.
Yeah.
The Gauss law is the easiest way to identify electric field at a point due to a complex charge system.
Yes. 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 See, out of these four Maxwell's equations, the last two equations are very important. Okay. The last two equations is what gives the relations for electromagnetism. Okay. Fine. So similarly, we do have Gauss law for magnetism, and also with the third law and with the fourth equation, we can make electric field by changing a magnetic field. Okay, and this was even experimentally proven by Michael Faraday as well. Okay, well, and also coming to the fourth equation, we can make magnetic field with a changing electric current or with a current, just with the current. Okay, so this is the simple Maxwell's equation, and with the help of these Maxwell's equations, only all the electromagnetic waves are actually functioning. Okay, so there is also a meme which says that once upon a time God said, "Let there be a light," and they show these equations, and then at the end there will be a statement called as, "Okay, there was a light." So it's something related to that actually. Okay, but okay, meantime, coming to the Maxwell's equations. Okay, Maxwell's equations basically determine the flow, the behavior of the electromagnetic waves, how they are generated, how they are interlinked with the magnetic and electric behavior of the electromagnetic waves. Right? Yeah. Similarly, now coming back to these photos again, we are having something called as magnetic field here. Okay, right. So we are trying to explain the magnetic field with the help of guys turbulence model. Okay. Now the turbulence model basically stands with one key important equation in the fluid mechanics. Can anyone tell that? One key equation in the fluid mechanics. Without that, the fluid mechanics is literally near to zero. Anybody?
Bernoulli's equation.
Bernoulli's equation. Okay. Okay. Bernoulli's equation is the beginning stage. Can say. Okay. Other than that, one fluid mechanical equation without which the entire fluid mechanics would be equal to nearly equal to zero, you can say. The Navier-Stokes equation. Yeah, heard of this, guys?
Yeah. Now I stuck with this study.
Yeah, the Navier-Stokes equation. Okay, what does it say basically? Okay, what is it actually? So we'll have a look at that first. Okay, before that, we'll come back to Newton's law. I hope everyone in the call know about the Newton's three law. What does Newton's first law say? Everybody continues to be in a state of rest or in a uniform motion unless it is compelled to change that state by an external force. Right? This is the Newton's first law. Newton's second law is in front of you. It's basically F equal to ma. The force what we are putting is equal to mass into acceleration of the object. Okay, fine. Coming to Newton's third law, to every action there is equal and opposite reaction. Fine. But how come this is interrelated with the fluid equation? Okay, well, the fluid equation or the Navier-Stokes equation is basically the behavior of fluid mechanics or the fluid particles. If we are trying to give some amount of acceleration to it, some amount of force to a fluid at a particular amount of time, suppose let's say here you can see the turbulence. Determining this turbulence models, we are defining the boundary conditions, initial boundary conditions and the end point boundary conditions. So in the initial boundary conditions, if we are providing some amount of force in the form of pressure, in the form of viscosity, in the form of velocity, initial velocity. Okay, so when we are trying to provide those things, if a equation is able to predict what it might happen in the near future, then such kind of equation is very much relatable and analogous to Newton's second law. And that's what Newton's second law is telling us. Okay, if we are providing certain amount of force to a mass whose mass of a body whose mass is m, then we will be having certain amount of acceleration a. Right? It is used to make the predictions. So similarly, if we are trying to make the predictions in the fluid mechanics, okay, we will get in analogy with the Navier-Stokes equation. Okay, here you can see guys how the Navier-Stokes equation is actually, okay, how it is analogous to the Newton's second law, to be very frank. Okay, you can see in the blue is mass, the purple is acceleration, and the orange is force. So basically it is F equal to ma. The force is the internal stresses of the forces, the external forces, whatever it is been acting, and the internal pressure gradient of the fluid. When all these things are combined, okay, when all these things are combined to become the force of the fluid, okay, whenever you are pouring a fluid, whenever you are trying to um, bath, okay, whenever you are trying to drink a tea, all these forces are being acted. Okay, when a river is flowing, when you're trying to fill up the bucket or a bottle, all these forces are being acted. Okay, along with the accelerations, you can see the acceleration is in the form of partial derivatives. Okay, along with the mass. Okay, in the fluid we are having the mass in the form of density, right? So that's why we are considering the masses in the form of density here. Okay, so that is the whole agenda. Okay, that is the whole agenda of the Navier-Stokes equation, which describes the flow of incompressible fluid. Well, there is something called as compressible and incompressible fluid. Can anyone tell me what is that incompressible fluid and why we are trying to use only incompressible fluid in many of the applications? Yeah.
Compressible fluid's density doesn't change, and it eliminates a variable, unnecessary variable. If you consider
See,
incompressible fluids.
one thing is coming to compressible and incompressible fluids. Okay, coming to incompressible and compressible fluids. Compressible fluids are something whose volume can be compressed, basically. Okay, but not with the incompressible fluid. Suppose, let's say, if we are having a water, okay, we cannot compress it or we cannot decrease its volume, but for gases we can do it with the amount of external pressure. Okay, generally for gases. Okay, generally for gases, and even for some amount of fluids, we are considering incompressible fluids. We are considering them as the incompressible flow. Okay, we are considering them as the incompressible flow because we cannot compress it, especially for the fluids. Okay, so when these equations, when the Navier-Stokes equations are combined with, okay, are combined with Maxwell's equations, okay, when Navier-Stokes equations are combined with Maxwell's equations, we will be getting something called as magnetohydrodynamic equations. Okay, we will be getting as magnetohydrodynamic equations, and those equations are the combinations of Navier-Stokes equations and Maxwell's equations. Okay, I will just a second. I will share my screen. I will show you those equations, how they actually look like. Yeah, I hope my screen is visible, guys. Hello. Yeah,
It is smaller.
dynamic equations, guys. Okay, you can see all the partial derivatives has been combined. Okay, all the Navier-Stokes components are combined with the electromagnetic equations of the Maxwell's equation, and then we will be getting how the plasma is flowing, how the magnetic field is generated by the plasma that is being flown. Well, out of the curiosity, I'm having one question for you guys. Okay, so there is this saying. Okay, it says that magnetic field does not exist at hot temperature, right?
Yeah.
Okay, then how come earth is generating, or else even the sun is generating magnetic field? It is so hot, very high heat over there. How is that possible? Yeah, well, it comes from the magnetohydrodynamic concept, guys. Okay, moving charges generates electromagnetic fields. Okay, irrespective of their temperature. Maxwell's equation does not give any relation with temperatures. It gives the relation between magnetic and electric field. That's it. So as the electric and magnetic field, the charge carriers are just moved from one place to another place. Okay. What happens is, in the earth core or even on the sun's surface, the charged particles, the high energy ions, the plasma particles, okay, what they do is they move around in a chaotic way, in the turbulence way. And in the same way, magnetic field also is being generated. Okay, and with that magnetic field, electromagnetic waves also being generated correspondingly. Okay, So there is a lot of interrelation between fluid mechanics and the magnetic field, the Maxwell's equation, and the electromagnetic theory. Okay, so if we can sum up and bring up a good relation, and if we can model, so we can actually model the complete stellar evolution out of it. Okay, from the birth of the star to a death of the star, how the magnetic field is being varied, and how the surface of the star is being vanished, and how the gases are being interacted, at what particular point of time the magnetic fields are getting exploded, just like solar flares in case of sun. Okay, so they are being modeled with all these magnetohydrodynamic equations. So yeah, this is about today's topic. Actually there was a lot more to talk, but since there are only constrained participants, so we'll be limiting to only this amount of topic as of today. So will be continued based on the participants in the upcoming days. Yeah. So that's it from my end. So any other questions or queries related to this or apart from this, feel free to ask, guys. Yeah.
Actually, my work is actually in the reverse way. I'm not trying to produce magnetic field depending upon the movement of charged particles. But depending on the magnetic field, I'm trying to predict the movement of charged particles. Can you able to understand?
Based on the sorry, I could not understand.
No, my work is actually
Okay.
you said magnetohydrodynamics is about producing magnetic field depending upon the turbulent motion of the charged particles, right?
Yes, yes, yes.
Okay, but thing is, I have in my work, I'm having a standard magnetic field.
Hmm.
Okay, I'm trying to predict what is the motion of charged particles in the given magnetic field.
Okay, okay. In the
It's
given,
just reverse, man. Yeah,
yeah.
it's just reverse.
Oh, it's a reverse. It's a reverse. That's it. It's a reverse. You can use the same topic over there as well.
Yeah, but the thing is, my work, the difficulty I'm facing is,
Okay.
uh, I'm trying to design my own magnetic field, own structure of magnetic field. Like I have created something called a modified Helmholtz coil.
Mm-hmm.
But the thing is, when I'm trying to do simulations, I'm not able to produce proper magnetic field. I'm trying to do my simulation in Python. In that Python, I'm using a Magnetohydrodynamics library.
Mm-hmm.
But what the actually the practically whatever the magnetic field is supposed to come, that
Hmm.
Magnetohydrodynamics is not giving that magnetic field. There's something wrong in that library, I guess. Or I don't know what's happening.
So
So
you are using matplotlib as a function, right?
no, Magpylib. There
Mat.
is a
Okay.
Magpylib.
Okay. Matpylib. Okay.
Yeah,
So
Magpylib.
I hope there would be some inbuilt magnetic function simulations or the fluid simulations in the Python that already been existed as a module. Let's
Yeah,
see if we are having any such kind of modules that we found across. We will be sharing that to you. That would be helpful for you.
yeah. Please, I was looking for that very badly for long, 1 year, for last
Okay.
1 year.
Sure.
So
And is there any particular characteristic of that magnetic field that also you can give those details so that we can try and help you with that. Yeah.
yeah, it's nothing. It's a Helmholtz coil is like a two circular coil. You know about Helmholtz coil, right?
Hmm.
Yeah, two
Okay.
circular coil at a certain distance between them.
Yeah.
That's
Yeah.
Helmholtz coil. But the thing is, my variation is Helmholtz coil at a different radius.
Mm-hmm.
So the thing is,
Fine then.
I'm not able to create the modified magnetic field in my Mac in Python. But if I created, it will give a different value, which is getting opposite to the actual prediction that we made in some other simulations. So the
Okay.
thing is,
Okay.
I need help in building my own magnetic field in Python simulation.
Understood. Understood.
Yeah,
Fine. No problem. If we are having any, if we come across any such kind of programs or inbuilt Python modules, so we'll be sharing that to you. So please, I mean, you guys are having contact details, right? You can contact and you can ask as well if possible.
yeah, sure.
Fine. So any other queries, guys? Any other questions? Yeah. Fine then. Nothing from my side as well. Fine, Dhanush, we'll close it today. Yeah.